Afternoon, grade 10s. I hope you're doing well and that you have truly mastered the electrostatic circuits section that we did before. Today we started with electric circuits on page 147, and electrical circuits is something that can be very, very tricky if you don't understand it. So there's a lot of formulas, there's a lot of scenarios and question types that they can ask you, but if you understand the work, the theory behind it, the reason for the formulas, the way they are, etc., then you'll be fine. Because memorizing all the different formulas, there's a lot of formulas, and you can't just always apply them. You need to think a bit further than just write down a formula and plug in values. So you must understand it's very important for this section. And you've done circuits before. Grade 10 won't have too much extra compared to previous years, but the complexity will increase definitely. So it will be a lot harder than the previous year's circuit questions. Alright, so let's first of all start off by talking about electric current. Electric current, I, is the rate of the flow of charge. Rate meaning the time, how fast or slow, so fast or slow, does electrons flow. So charge is electrons. Remember, we did charge quite extensively just now in our electrostatics course. How fast or slow does electrons flow through a circuit? So I is my current, and it's measured with an ammeter, an instrument that we use to measure that in current, and then the unit is ampere, and the symbol for that is just simply A. Alright, so current is equal to charge, coulomb, per change in time, in second. But these aren't that important, these two. You must just focus on your current, and that it's charge over change in time. Alright, so it's how fast does my charge flow through my current, my charge flow through my circuit, excuse me. Alright, so let's take a look at just a straightforward circuit that we have here, and we're looking at conventional currents. I'll mention that just now. So as you know, the longer edge and the shorter edge of a cell indicate whether it's positive or negative. Longer line means it's positive, and conventional current, we assume that the current flows from positive to negative. So the current flows straight through my circuit all the way here to this bad boy there that we call a resistor. Now in previous years you used resistors, but you also spoke about, you see on the right, we spoke about light bulbs, and you use this X to represent it. Well, from now on we won't really be using X's that much. Your textbook does use it for a bit to help ease you in, but we'll be using this rectangle over here to indicate resistors. Now resistors are anything that give resistance to the flow of current. So it's harder for the current to actually flow through a resistor. And it actually loses energy when passing through a resistor, and that energy is actually given off in the form of light or heat, etc. So olden days light bulbs actually lit up because of the high resistance of the filament that we use. These days we use fluorescent bulbs. Some stoves still use high resistance filaments to heat up if you don't have a gas stove, etc. So resistors convert electrical energy to light or heat or sound or anything like that. So anything where there is a conversion of electrical energy to something else, then you'll find that it's a resistor. Okay, and then here we have my ammeter, which is always in series. It's got a low resistance, and it's always in series. And your switch, which will just close up there. Alright, so my current that I'm speaking about is the flow of electrons. Now, we mustn't think of the flow of electrons, the current, as I'm opening a tap over here and suddenly electrons move slowly along until the end, through all the way to the end. These electrons that are flowing through are delocalized electrons, meaning they are on the outer energy levels of our atoms. They delocalize, they're free to move. They're free to move between my copper atoms. We usually use copper for our circuit wiring. So these electrons can move easily from one side to the next, and they are abundant they're abundant throughout the circuit all the way through. Alright, so what happens is when I switch on my circuit or I insert the battery, these electrons start moving slowly in this direction. Well, we assume that direction with conventional current, but it's not as if I open a tap here and suddenly the electrons just start flowing, and before there wasn't any electrons here. The electrons are there anyway. It works in the principle of one electron is introduced here, and that pushes the rest along. There's a pushing force, the battery has a pushing force, which pushes the electrons along through my circuit until the end, where this electron is then moved back in. Alright, so it's important to have that concept of electrons, as they don't just open up and they all come from here. They're already there, but there's a force that pushes them along through the circuit. You must make a note of that. You must remember that. And when I'm speaking, let me speak about the conventional current. Conventional current tells us that current flows from positive over here to negative. In reality, current actually flows all the way from negative through to positive. But due to the history of circuits, and originally people thought that it flowed from positive to negative, we are taught at high school level that we use conventional current, which flows from positive to negative. The actual current we call electron current, which is negative to positive. I hope that makes sense. But you must just keep in the back of your mind, all you have to do is keep in the back of your mind that actually the electrons are flowing opposite to what we are saying. But we just deal with it as if they're flowing from positive to negative. Alright, let's speak about potential difference over here. Potential difference, or EMF, electromotive force. We use them interchangeably at grade 10 level. But potential difference, V, it's not voltage. We call it potential difference in science, is the energy that the electrons have. It refers to the energy that the electrons have. So this is work, or the energy, which is measured in joules, and this is charge, which is measured in coulombs. So potential difference, the unit is volts, and the symbol for that is V. Alright, so we deal with that. So what it says, potential difference, is if I have a battery that is 12 volts, see at the bottom, that means that each 1 coulomb has 12 joules of energy. It's the energy that the electrons have. But we're dealing with potential difference. Remember, if I say difference, I have to go and subtract something. I started with a certain amount and I have to subtract the rest. So what a voltmeter does, a voltmeter over here, it measures in parallel to my circuit. It measures the potential energy, the energy of my electrons at one end and at the other end, and then it measures the difference between the two. So the energy of my electrons here is different to the energy of my electrons there. Why? Because we have a resistor right here. So these electrons are flowing through, all the way through, straight to there. Now if I go take a look at this electron right before my resistor and after my resistor, this electron had to give off energy to pass through a resistor, because resistors make it tough for electrons to flow through. So the energy of the electrons before and the energy of the electrons after is different, and my potential difference between the two is measured by my voltmeter, and that's where that comes from and why it has to be in parallel. Now remember, just another note is a voltmeter has a very high resistance. Very high resistance. So we must make sure that we don't put it in series, otherwise your circuit won't work. Okay, now series versus parallel. We must remember, we must be able to distinguish between series and parallel. They can get very confusing. They can throw you some pretty tough looking circuits in your direction when you're busy with circuits in grade 10, but you must be able to distinguish when is something in series and when is something in parallel. So let's take a look over here. Here my current is flowing from positive straight through one resistor, second resistor, all the way to the end. So my main current is the same all throughout. Nothing is changing. But on the right hand side, my current is flowing until it comes to a junction where it splits into two different currents. And then they join again, and then that main current there is the same as the current before. Right. Now the amount of current going into each branch actually depends on the resistors themselves. So in parallel, if the resistance increases, so the higher resistance, so let's say for example this one is 5 ohms and this one is 3 ohms. The higher resistor will actually get a lower current. Okay, and I'll expand on that in a bit. But the higher the resistance in parallel, the lower the current that will flow through it. So the opposite is also true. If the resistance is low, the current flowing through it will be higher compared to another resistor. Okay, so let's just take a look at identifying when is something in series and when is something in parallel. Now this first one, my main current is flowing through. That's a series resistor. There's nothing else connecting it. And what happens here, I have a point where my current is split. So these two resistors are in parallel to each other. They meet again to the end. You must just be able to see. So they don't always have to draw it the same way. But the moment you see a split in your circuit, you must be able to identify which resistors are in parallel to each other. Same in this example, current is flowing through. At this point there's a junction, it splits and it goes the other direction as well, and then it meets up again, the main current finishes off. And here I just made that note again saying that the higher the resistance, the lower the current. So if these were all three identical resistors, all of them 1 ohm, the branch at the bottom would have the higher current. The current here would be higher. And this is a higher resistance, so it's 2 ohms, so the current would be lower. Alright, so just remember, if this is confusing to you, you got lost, pause the video, just listen to it again, take a look at your textbook. There's also nice explanations there. Message me, just let me know, because this work is a bit tough, but we just need to practice it in. Alright, let's take a look at this one as well. And this one is especially threatening, but we mustn't be threatened by it. We have our finger, so you just put your finger down, follow the currents. What happens at this point? It's split into 2. So there's one branch and it meets again there, and here's the other branch and it meets at the same end. So this circuit here can be represented in exactly the same way as the one on the right hand side. So the left and the right is the same thing, just different ways of representing it. So go taste for yourself, go back to the previous one, see if you can follow along with your finger. Where does the current split up, and how do we know that these resistors are actually in parallel to each other? Alright, that's important. Alright, so your formulas that you need to use for electrical circuit, your calculations are as follows: V equals I times R, your potential difference, your current, and your resistance. There's 3 variations and you use them as needed. Alright, this is actually called Ohm's law, but I'll discuss that a bit later in more detail. This equation here is Ohm's law. Alright, so let's take a look at this example, the first example. where they give us a simple circuit. So we must be able to identify what's given to us. It flows from positive to negative. What's this? An ammeter, right? And it tells me the main current. This is my main current. The main current is actually 1 amperes. Right, so that current is flowing through. What's here? There's one resistor of 2 ohm size, and there's another resistor 1 ohm. So the current through all of them is the same. There's 1 ampere of current flowing through and 1 ampere there. Remember, what does 1 ampere mean again? 1 ampere, it means coulomb per second. Coulomb per second is per second, yes. Because my current is actually charge over time. So what does 1 ampere actually mean? It means that in 1 second, 1 coulomb passes that point. Okay, just keep that in mind. It's not just something we made up, it actually represents something. And that's the same straight throughout the circuit. Okay, so let's just quickly answer this question, the first one here, where it says, what is R total? Which means the total resistance of the circuit. Okay, so how will we calculate that? Simple enough. In series, we add the 2 resistors together. So it's R1 plus R2. The first resistor is 2 ohm plus 1 ohm. So the total resistance is 3 ohm. You've done this many times before. Not much to it. Okay, next one, they ask us, what is the total potential difference? So we'll use the formula at the top, V equals IR. What's the current going through my circuit? It's 1 ampere. What's the resistance? For the whole circuit, we just calculated it's 3. So my potential difference is actually 3 volts. Okay. It's important to remember, you must write down your formula, substitute, and then write with the unit as well to get all of your marks. Otherwise, there's not much of a point to it. Let's continue to the next example, which is a bit trickier, but let's just take a look. Don't be too threatened by it. They tell us that the main current is 4 amps. It's given to us by that ammeter reading at the top. Here I have a single resistor. Let's check what happens. So I have a single resistor, that's in series. Over here, I have a split. What does this branch do? Oh, that's a voltmeter, so there won't be any current going through there. Over here, 2 ohms, they meet again, and then they continue. Okay, so now we must take a look. What happens to the current here at the point where it splits? We'll discuss that just now. What they're asking first is, what is the parallel resistance total equal to? So RP is the parallel resistance. It's these two together. Well, the formula for parallel resistance is 1 over Rp equals 1 over R1 plus 1 over R2. We must use the inverse. We must remember to use this only for the parallel resistors. So 1 over Rp, what's my first resistor? It's 2. The second resistor is 2. So total is 1. Alright, I'm just going to quickly shift it a bit to the side. I'll talk about this X now. Okay, so we must say that we can see that 1 over Rp is equal to 1. Now in this case it's pretty simple to find the inverse because Rp will just be equal to 1. But when you'll be able to use your calculator, I'll quickly show you the steps. Alright, so when doing this, we say 1 over 2 plus 1 over 2. Just put your answer. And then near the top right corner of your calculator, there's actually an inverse. So you press answer, or you press inverse there at the top right, and you just say equals to 1. But obviously the inverse of 1 over 1 is equal to 1 over 1 if you split it around. So your parallel is 1. But let's say I had something like 1 over Rp equals to 3 over 4. Now it's pretty simple, but just to make sure with our calculators, you can say your answer is 3 over 4 equals, and just say inverse of answer equals 4 over 3. So what that will mean is Rp is actually 3 over not 3 over 4, sorry, 4 over 3. You must be able to get the inverse of your resistance. Okay, so now, what is the parallel resistance? It's actually 1. Okay, the total there. You must be able to calculate that, and we'll get to more examples just now. So, next they ask what happens to the current. I discussed that already. It gets split up. The current is 4 amps, right? These two resistors are identical. So the amount of current that will go into each branch will be the same. So if I have 4 amps and it gets split into 2 of the same, of 2 branches that have the same resistance, it means that 2 amps will flow through there and 2 amps will flow through there. Exactly the same. Alright? That's important to know, but it's only applicable if these 2 resistors are the same. So let's take a look at the questions. They're asking, what is V1 equal to? That's my voltmeter over there. Let's take a look. So V is equal to I times R. We must know that by now. I is 4 amps going through there, and R is actually 2 ohms. So it's 4 amps times 2 ohms, which is 8 volts. So here we have 8 volts. Alright. Next they're asking V2. What is my friend over here equal to? Well, we'll just do the same, which is I times R. I, in this case, is 2 amps times 2 ohm, which is 4 volts. Okay. And if we do the same for V3, we'll see it's exactly the same. So V3 is also equal to 4 volts. But next they ask me, what is V4 equal to? V4 over top, over here at the top. Right, that's V4. Well, we'll see that V4 is actually over both in parallel. Okay, so V4 is also I times R. What is the current that's flowing from the point here? How much current? 4 amps. And there it's also 4 amps. We add those two together. So the total current flowing through there is 4. And the resistance, what's the parallel resistance? We calculated as 1. So V4 is actually also 4 volts. This is important to note because 4 volts there. So the total voltmeter reading over the parallel resistors, over both of them, is 4 volts. This one is 4 volts and that one is 4 volts over here. It's important to note because this will always be the case that the potential difference in parallel will always be the same. If this branch is 4 volts, the other branch will also be 4 volts. And the total over will be 4 volts. It's going to be the same always for parallel. Okay. Now let's quickly take a look here at this question, where we see that we have a circuit with a potential difference of 26 volts. There's a main current of 3 amps. There's an 8 ohm resistor here, 10 ohm and 5 ohm. Okay. Now, we must speak about what happens to the current. The current is flowing through here, still in series. At this point, there's a junction where it splits. Okay. Now, I spoke about it. There's a 10 ohm and a 5 ohm. Which resistor will have the smallest current flowing through it? It will be the 10 ohm one, because the larger the resistance, the smaller the current. Okay. But I want to go calculate what the current is that is flowing through each of them. This calculation isn't too tough, but don't break your brain too much. I just want to quickly explain to you what happens if the two resistors are not the same. The first one is 10 ohm and the other one is 5 ohm. So the ratio is 10 to 5. If I simplify that, dividing by 5, it becomes 2 to 1. So basically, whatever current is flowing through my 5 amp will be double the current that is flowing through my 10 ohm, not 5 amp, 5 ohm. This current here will be twice the current at the top. Okay, it's inverse. It's very important. So how much amp do we actually have? We have 3 amps. Well, how will I divide 3 in a ratio of 2 to 1? It's quite simple. This one will be 1 amp and this one will be 2 amp. There's actually a way to go calculate it, etc. But the main purpose of this is to show you this ratio, 2 to 1. So then 2 plus 1 is equal to 3. It will be 3 amps. If the current was, for example, just for argument's sake, it wasn't 3 amps, it was 6 amps. What will we do then? Well, the ratio is 2 to 1. How will I get that in a ratio that I can get to 6? Well, 3. Well, it would be 4 to 2. Right, I just double the ratio. 4 plus 2 is 6. So then it would be 4 amps and 2 amps. Alright. This is just to give you an explanation of what happens to the current when there's unequal resistors in a circuit, in a parallel circuit. Okay. Don't break your brain too much over that one. I just want to get the idea into your head of what happens to the current. Okay, then let's get to Ohm's law. After this, I'm going to do a quick example with you, and then you can get to the homework and try that out. Yeah, hopefully this is good enough to help you guys out. If you do get stuck, please let me know, and we can see what else we can try. So Ohm's law states that the potential difference of a circuit is directly proportional to the current at a constant temperature. So potential difference directly proportional to current. What does directly proportional mean? It means as the one increases, the other one will increase. So if you took a graph and you measured the current and the voltage at the same temperature, if I increase the voltage, the current will increase as well. So if it's 10 and it's 2 there, if I increase the voltage to 4, then the current will double as well. So from 10 to 20, etc. So the ratio, the relationship between the two is directly proportional, and it means as the one increases, the other one will increase. And in a graph, you'll get a straight line. Usually you do an experiment on this in grade 10, and in the current circumstances, I'm not sure exactly when that will happen, or even if it will happen. Alright, so that you must just keep in mind, Ohm's law is the reason we can use this formula, and you must know this definition off by heart because it gets asked quite often. Now I'm going to do a question out of exercise 13 in page 167, question 4. This is in your textbook, so please follow along. If you feel like you can try it on your own already, then go for it. Pause the video as you go along. But I'm going to do this step by step with you now. So 4.1 asks me the parallel resistance. Well, I know that 1 over Rp is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Where am I looking at? I'm actually looking at these 3 resistors right here in parallel to each other. 2 ohm, 4 ohm, and 6 ohm. So if I substitute that back in, 1 over Rp is equal to 1 over 2 plus 1 over 4 plus 1 over 6. Alright, and let's just quickly jump to the calculator to help us out there. So I'm going to say 1 over 2 plus 1 over 4, and you must do this on your calculator as well because you must practice this. 1 over 4 plus 1 over 6. That's all of them. I just say equals and the inverse. So then I can directly say that Rp is equal to, let me just double check there, it's 12 over 11. If I take that to decimal, it's 1.09. Okay, so I round it off to 2 decimals, 1.09. That's my answer to the first one. What unit do we use? Ohm. Okay. So I'm going to erase that out a bit so I have space for the next question. I'll just put the answer back. Okay. So I calculated it's 1.09 ohms. You must write down the formula, substitute, get your answer. Alright. Next, what is a 1 over here? we can see that it is my main current, and they tell us that the potential difference of the battery is 12 volts. Alright, so how we calculate this? Well, we know that I is equal to V over R. What's the potential difference? In this case, it's 12. What's the total resistance? It's 1,09. If you put that into your calculator, we get an answer of, I think it's 11. Let's just double check. 12 over 1,09. Yes, 11.01. Okay, so we get 11,01 amps. Rounded off to 2 decimals. So that's my answer, 11,01 amps. Alright, next one, 4.3. What is the potential difference of the parallel? What do they mean by that? The potential difference of the parallel branch is, what is if I had a voltmeter like this across the whole thing, what would that voltmeter be? Okay, well, simple enough. V is equal to I times R. What's the current that will flow through all of it? If I add all the currents together, well, we just calculated that current, the main current here, as 11,01. So after adding all these currents together, you'll get 11,01. So it's 11,01. What's the resistance of the parallel? Well, the resistance of the parallel we calculated is 1,09, right? And if you just put that in your calculator, you'll find an answer of 20,92 volts. Alright. Let me just double check that I did everything right there. Gonna do something. Let me just quickly check. I think I made a mistake in one of the steps. I did this beforehand. No, that's something else. Yes, 11. Yes, I think I made a mistake just in my calculator now. Oh yeah, it's 1.09. Sorry guys. Let me just quickly correct that. It's not 20. I want to say that doesn't sound right. If we put it in, the answer is 12. The answer is actually 12 volts. 12,00 volts. Alright, so this voltmeter here would have a measurement of 12 volts. Meaning what exactly? Remember, it's joules per coulomb. So meaning that 1 coulomb of electrons used up 12 joules of energy going from this point over here to this point over there. Okay, so that's the meaning of them. Next question, question 4.4 is asking us, out of the 3 currents, A2, A3, and A4, which one has the greatest current flowing through it? Well, I told you many times before now that the greatest current goes through the lowest resistor. So the answer here is the 2 ohm resistor. Right. Because it has the lowest resistance, it will have the greatest current flowing through it in the parallel. Okay. 4.5, what is A4 equal to? Well, I'm going to write down the formula. I is equal to V over R. Right? And then they ask me, A4 is the one here at the bottom. What's the resistance there? You can substitute that in. The resistance is 6. What's the potential difference? Well, I calculated the potential difference here at the top to be 12. And I told you previously, if that potential difference is 12, this one will have a potential difference of 12. Here we'll also have a potential difference of 12, and this one will also have a potential difference of 12. In parallel, all of them will be the same. So I can substitute that as 12, which gives me 2 amps. The same with A3, I is equal to V over R. The voltage will be 12. A3 just has 4 ohms. 12 over 4 is 3 amps. Alright, now you can check your calculations, because we see this one here is 3 amps, this one is 2 amps, other way around, this one is 2 amps, this one is 3 amps, and then lastly, what will this one be? Well, the total current is 11, so 2 plus 3 is 5, 11 minus 5 is 6, so I can already tell you this one will be 6 amps. Because in a parallel circuit, these 3 currents must add up together again to give me the total. Right, that 0.01 is there due to a rounding, not error, due to the rounding that we did in a previous question. So 2 plus 3 is 5 plus 6 is 11. So this current plus this current plus this current will give me my main current. Remember, it branches into 3, we add them together, and then we get the main current again. Okay. Now they ask us what happens when the 2 ohm light bulb blows out. What happens to the main current, to A1? Well, if my light bulb over here blew out, what would happen to the current? It will in fact decrease. Right? Why will it decrease? Well, let's just take a look what will happen to RP. RP is 1 over 4 then, plus 1 over 6, right? Previously it was 1 over 2 plus 1 over 4 plus 1 over 6. If this light bulb blows out, my parallel resistance will change. So if I calculate those two together with your calculator, you can also just use good old-fashioned mathematics. 3 over 12 plus 2 over 12, which is 5 over 12. And if I take the inverse of that, RP is equal to 12 over 5. Which is equal to 2,4 ohm. Let's quickly take a look at the previous one. We calculated as 1,09 ohm. Now it's increased to 2,4 ohm. So taking a resistor away has actually increased the resistance. This happens when you take a resistor out of parallel. And they're asking what happens to the current. Remember, I is equal to V over R. Right? The voltage stays the same, it's still going to be 12, right? But the total resistance actually increased to 2,4 now, which means that my answer will be 12 over 2,4, 0,5, 12 over 2,4, 5, is actually going to be 5 amps. What was my current previously? 11 amps, it's decreased to 5 amps. Alright, depending on what they ask, you don't always have to show these calculations, but this is just to help you understand why it will decrease. So what happens when the light bulb blows? The resistance increases, you can see it's more, and using this formula here, I equals V over R, we can see that the current will actually decrease in comparison to the previous 11 amps. I really hope that helps you out. If it doesn't, let me know. Please give feedback so we can help each other out in these times. Yeah, please let me know if there's anything I can do. I want you to go and try exercise 13, question 2, 3, and 5 for Thursday. Please speak to me, communicate with me, what you're struggling with, etc., and then I can help you out. So just those 3 questions, you should be able to do them by Thursday. All right. I hope you have a wonderful day. You're enjoying your week. And yes, thank you.